All right, today we're going to look at some variations on this greedy descent. So what we're going to do is we're going to select a variable to change and a new value for it. So here are a whole lot of choices that we can do. We could do the most improving step. We could find the variable value of fair that minimizes the number of conflicts. Okay, this seems like the best thing to do, but you want to think about is what data structures are required. We'll talk about this in class. So think about what data structures you require to do this. We could do something simpler. We could select a variable that participates in the most conflicts, and then we could select a value that minimizes the number of conflicts. So then you could ask what data structure is required for this. And the third choice here is any conflict. We're going to select a variable that appears in any conflict and select a value at random. Okay. What data structure is required for this? So think about what data structure you require for each of those. Another one we could do is you could just select a variable at random and select a value that minimizes the number of conflicts. And then you can think about what data structure is required to do this. And then you can select a variable and value at random, accept this change if it doesn't increase the number of conflicts. So here's a whole lot of choices we could make. The top ones seem to be the most greedy in trying to make the best effort to do the upward steps, but think about what data structure required and also how to maintain those data structures as we act. Okay, all right. So one measure of assignment is the number of conflicts, but often we want to weight some conflicts higher than another. So why would we do that? Well, and some are easier to solve. For in the scheduling exams, maybe we'd like to, some things are more important than others, are harder to move. It's very hard to move a very big exam. So maybe we should try and, assign those first and then give those higher weight. Or maybe there's lots of other things we could think about that some things become, we want to make it harder to move some of those things. And if H is an assignment, total assignment, define H of A to be a measure of the difficulty in solving the problem from A. So if H is 0, then A is a solution and lower H is better. That's what we're really going to do. We're going to choose this value so that we're going to try to minimize H. So it sort of tells us how hard it is to solve things. We're going to try and do the biggest steps, which we're going to solve the most difficult problems first. So there's one variant of this, which is called simulated annealing. We're going to pick a variable at random and a new value at random. And if it isn't worse, we're going to accept it. And if it is worse, well, what should we do? Well, we could just reject it. But instead of doing that, we're going to accept it with some probabilistic, depending on something called a temperature parameter T. So with the current assignment A and the proposed assignment A prime, we can accept it with this probability that's an exponential of the differences in the heuristic value divided by the temperature. Now, temperature tells us how sensitive it is. And the thing you should notice here is that if it's an improvement, so if A prime is worse, then this is negative, so this is less than 1, right? So it's positive, this is greater than 1, and we're just going to accept it. So it's not really a probability, but we're just going to accept it. Okay. So now let's look at what this temperature does. So the temperature really tells us the probability of accepting a change. So we're just going to look at integer changes. So the temperature of 10, right? If it's 1 worse, it's going to choose it 91% of the time. And if it's 3 worse, it's going to choose it 74% of the time. So this lets us have a slight preference for fewer things worse. So we're going to reject some of these things that end up getting a lot worse. So this lets us jump around in the space and sort of do lots of exploration. As the temperature is 1, then 1 worse is accepted 37% of the time, but 3 worse is only accepted 5% of the time. So here we have sort of we're much less likely to accept something that's 3 worse. And as the temperature here gets to be 1/4, we're really only accepting things that are 1 worse 2% of the time, and we're very rarely accepting things that are 3 worse. And if the temperature is 0.1, then 2 worse, we accept it with probability very unlikely. So acceptably, At a temperature of 0.1, we're very, very occasionally accepting something that's one worse. And here we're basically being greedy. We're just accepting the best one at all times. And often what happens is we reduce the temperature. We start off at a high temperature like 10, and we walk around then, and we have it gives us a slight preference for better things and good things. And as we go along, we start committing to more things. And so as we start committing to more values, steps that become worse are accepted less often. Okay, so there's one variant. Another thing we can do is what's called a random restart. A random restart involves reassigning all the values to variables at random. And why we do this is allows for exploration of a different part of the search space. And it's also interesting because we can do it analytically. So each run is independent of the others, so we're going to just completely restart everything. And because of this, the probabilities can be derived analytically. So let's suppose that each run has a probability of p finding a solution. And we do n runs until a solution is found. So now the probability of n runs finding a solution, failing to find a solution, well, each of them has got to fail to find a solution, and they're all independent. So the probability of failing to find a solution is 1 minus p, and because of n of them, it's 1 minus p to the n. So this is because we're assuming that they're independent runs. And so the probability of finding a solution is 1 minus that. Okay, and if you plot this again, if the probability of it actually succeeding is 0.1, and we run it 5 times, we end up with a chance of 0.4. If you're this probability, even though each time it's around likely to find a solution, after 50 runs, it's likely to find a solution 99.5% of the time. Okay. If probability is 0.08, then after 5 runs, all of a sudden we've boosted it up to 3 in 10,000. This is right. And with 10 runs, we're getting pretty sure to do this. And at 50 runs, it's within numerical precision. So this is what Python gives me as this value for 0.8. It tells me it's 1. As far as Python is concerned, as far as the arithmetic in a computer is concerned, it's 1. Okay, so it's essentially guaranteed to find a solution in this bottom corner here. Okay, so even something you might say, well, something that doesn't happen, that only happens 30% of the time, that only succeeds 30% of the time is not very useful. Well, it's very useful if you can run it 20 or 50 times. You're essentially guaranteed to find the solution. Okay, so now we have this chance of saying, well, maybe we don't really need to maximize the probability. If it's fast, we can just run it lots of times. That actually works too. Okay, another issue you can do is you can prevent cycling. You can make a taboo list of the last k assignments. And then we just don't allow an assignment that's already in the taboo list. So we're going to not allow them. And if k is 1, we don't allow an assignment to the same value as the variable chosen. We just don't let us have the same value. We can use higher k as well. And it turns out you can implement it more efficiently in the list of complete assignments, particularly if k is small, because if there are a million variables and we've only allowed k as 10, we only have to check the values of the 10 things that were changed last. And as long as we're changing something different, then it won't be in the taboo list. Okay, and it can be expensive if k is large. So it seems like, right. Another thing we can do is for complex domains. So if domains are small and unordered, the neighbors of an assignment can correspond to choosing another value for one of the variables. However, when the domains are not small and unordered, we might need to do something else. So when the domains are large and ordered, the neighbors of an assignment of the adjacent values for one of the variables. You can imagine saying, for the sizes, we can imagine saying going from a medium to a large could be one step, and you got to see whether that improves it, because there might be lots of sizes in clothing, for example. So if the domains are continuous, we do something called gradient descent. Changes each variable proportional to the gradient of the heuristic function. So we're going to do the gradient tells us whether we're going uphill and downhill. So the gradient, so if you remember, for those who've done calculus, you remember that the gradient tells us the slope. If the gradient is positive, the slope is up. If the gradient is negative, the slope is down. So what we'd like to do is we'd like to go up or down and look at the gradients. That's what the gradient tells us. So the value of a variable vi goes from to in the opposite direction of the gradient. So if the gradient is positive, then it goes, we want to go down because we want to minimize. If the gradient is negative, we go increase it. And this eta is what's called the step size. And these neural networks do gradient descent with thousands or millions or even billions of dimensions of here to minimize the error on a data set. So 340, you look at gradient descent and its variance of actually solving large machine learning algorithms. But this is essentially an example of an optimization problem. Okay. The problem with gradient descent, and I tried to draw a diagram but didn't do it very well, but hope you can see. So these are supposed to be contours in a graph, and let's think about, because contours on the ground don't work for holes because they fill up with water and they become lakes. But let's imagine these are hills with contours on here. So now we have this one here as a local optima. It's not as good as this global optima, but if you try and walk around this area, you'll step around left, right. Any way you step right, it looks good. Unless you know there's something better, then it's hard to actually find it. So one of the problems you have to worry about is a local optimum that's not a global optimum. Another problem is a plateau where the heuristic values are uninformative. Enough of what we do in a plateau is if we're going up to a plateau and we get this value where it's all flat, then maybe we want to keep going until we find, because maybe it goes up somewhere else. So if it's uninformative, it might be better just to keep moving forward. So there's a heuristic that we're going to use for plateaus. Now ridge here is interesting. So if you're at this point at the bottom here, and no matter if you go up, down, left, or right, it's downhill all the way. So remember, trying to go uphill on this, we're pretending this is like a hill. And if you go up, down, left, and right, they're all downhill. They're all less than this point. However, if you did a one-step look ahead, you're up and then to the right, you actually find there's an uphill. So sometimes multiple step look aheads help on things that looks like ridges. So the other thing we can do is not just to look at one step ahead, but look at multiple steps ahead. And we're going to see when we play with some examples that just changing one variable doesn't help. But if we change two variables, it actually helps us a lot. And the saddle area is a special sort of plateau where essentially that if you look north-south, you're at the top, but if you look east-west here, you're at the bottom. So if you start moving up the hill towards the saddle, then you actually have to change directions completely. So saddle points end up being complicated you end up being one of the tricky problems in a lot of these algorithms that use gradient descent for optimizing. So it's hard to understand what's going on here. But let's look at this, two search spaces, and the idea is we can do a small step left or right. Imagine just going a few pixels left or right. And now, what method do you find the global maximum? And what would you suggest doing this? Well, you could do a random walk, but if you do a random walk, well, this one here gets stuck in here, right? You'd end up still wandering around. Sometimes you walk up and down. But a global random restart, well, some of the time you'll end up here and then you go down. So a global restart will actually work in this one. If you do this on the B, you can imagine a global restart, you always essentially get stuck in one of these jaggedy parts. So no matter whether you do a global restart that you go downhill, you always end up stuck in one of these. But a random walk will end up tending to get out of one of these. So you get down here, you can randomly step, and then eventually you will move down this slope because you're going to have both random steps and downward slopes. You could eventually get to this. These are just caricatures of what goes on, but in some sense, it's what can happen in these spaces, but they're really hard to analyze, right? So you get hundreds or thousands or millions of dimensions in here, and it's really hard to understand what's going on in these spaces. But nothing is best or overall. So what happens here depends on what the structure of the space. And then we have to worry about what if different parts of the search space have different structure. So that's another thing people worry about. So there are lots of issues that you have to be concerned about when you're thinking about designing a local search algorithm. Okay, thank you. Let's think about some more of these in class.